too many buttons to click. Oh, so sorry. All right, so after a month and a half of data, you're finally ready to hit counter of first graph. Very simple to specify 10 nodes. Say any relevant to the graph. There is an edge between U and B. Yes. P independently of everything else. Simplest possible random number. You can ignore. It's an abstraction for many interesting problems. It's not reality of any sort. So to visualize inputs that you want. You connect 3 to nodes. So on. So what is the immediate interesting question we're going to ask? What is the first thing that comes to mind? It's a complete description of the graph. There is nothing more to define. 2 parameters, n, the number of nodes, and p, the probability with which an edge exists between any 2 nodes.
For what p, I have a component. Big connected component.
Oh, how big? Big is how big?
In proportion to the number of nodes.
Okay, so that's the first question one wants to ask. It's also called a percolation question. Given that the total number of nodes is n, what is the smallest value of p for which the connected component size is of order n? That's one question one can ask. What else can you ask?
If the graph is small, then I could ask.
What is small and large?
Sorry, if we do not have a big cluster like
order n
cluster, then I could ask the distribution of small size cluster.
Okay. Essentially, you can just always ask the size of the cluster.
Yes.
That if I pick a typical node, so this word typical will keep appearing again and again to the post. Typical essentially means that you pick any one of these nodes uniformly randomly. What are you likely to see?
So a single node can connect to all other nodes, right?
See, it can, but that probability is how much? How small is that? P to the power n.
Close to 0.
That's not close to, it's p to the power n, whatever that p is.
But p is always less than 1, right?
Yes,
Yes,
that's true. But what you're really interested in is this possibly is connected. So you can go from, let's say, this is U, this is V, and this is W. So even though there is no direct edge between U and W, there could be a path
that connects
W via some other nodes.
Yes.
So this is how even for small p, you're actually going to get large connected components.
Okay.
So there is no direction to these edges. There's undirectional. If you can go from U to V, you also can go from V to U.
And we could relating to this, we could also ask given 2 vertices, using how many hops I can reach the other.
Right. So that's called the diameter. So what is called diameter of the graph is. So let's suppose there is a path between U and V. Let's call it d of U comma V, to be the number of edges of the shortest path. Now, across the whole graph, the diameter is defined to be, it's called D, to be the max over U comma V of little to a little d of V. This is called the diameter. That's what the farthest number of edges I have to travel so that I can go from any node to any other node. It's just a distance metric.
Okay. So U and V are like.
So in this case, U and W are connected by a path which has length 2.
Yes.
Right. Now suppose I connect this guy. Let's call this that. What's the diameter of this graph? Suppose these are all the edges there are. Can you tell me what the diameter of this graph is? So this is, let's say A, this is B, C, D, E. So these are my nodes and these are my edges. What's the diameter of the graph?
Infinity plus.
Infinity. It's not even connected because from A you can't reach anywhere. So by default we're going to define that to be infinity. Okay. But suppose I connect this just to make sure that it's connected at least. Now what is the diameter of the graph? So this cutting doesn't mean anything. Now what's the diameter of the graph? So which nodes appear the farthest? A and D? Right? Or C or C and B? C and D. B and B or B and C? B and C maybe. 1, 2, 3, 4, 5, 6. That's one way to go to from B to C. What about this way? 1, 2, 3, 4. So I'm always counting the minimum. So what's finally what's the worst possible pair of edges? Worst possible pair of nodes? 4. Sure. The edge is also 4. 1, 2, this is 3 itself. 3. And what about U, V, W, D, and E? What about U and E? 3. Okay, so looks like 4. So that's what diameter is. You look at all possible pairs of nodes, find the largest distance between them. And when we say distance between pair of edges, a pair of vertices, it's always the minimum distance of the shortest. So otherwise there could be so many paths from a particular vertex to another vertex. Okay, so we would like to find how large the diameter of this graph is as a function of P. Okay, so let's question number 2. Let's. What are the questions we would like to ask? First was percolation. What is the value of P for which you have a connected component of X, a connected component of size order n? What is the diameter? So suppose you choose a P for which there is percolation, that is the connected component of size order n. What do you expect the diameter to be?
No, but
so suppose my P is such that there is percolation in this graph. What do you expect the diameter to be? Finite. That's too loose. That's not giving me any information. Even constant. That's what you meant by finite.
Means it will be existing, like it won't be infinity.
No, nothing is infinity in this case. N is given to you.
Yes, like at least we will have the idea that the graph is connected. That's it.
so there is already given.
That's critical. That's too much you're asking for too much. See, the connected component gives you no information about the connectivity of the graph. Connected component is only asking, is there a connected component of size order n? It could be that half of the nodes are not connected, which is perfectly fine. My definition only asks me, for example, I say, what is the probability with which n by 2 nodes are connected to each other? I don't care about the rest of the n by 2, they will be complete disconnect. It will be isolated, I don't care. Right? It doesn't tell you anything about that. So, should I have essentially said that it's not sufficient inference? It's only when I ask you that there is connectivity in this graph, then you can start asking, okay, now given that I have connectivity, what's the diameter of this graph? So that's a very surprising result. Once you have connectivity in this graph, the diameter is 2. It's not a constant of this 2.
What the expected diameter is 2.
With high probability, the diameter is 2. What you can expect? Much stronger than that. It's an incredible result that you can essentially go from any node to any node in this ups. Once you have ensured that there is connectivity. Connectivity means that I can go from any node to any. That's when diameter makes sense. These questions, even though that looks very intimidating, are not that difficult to actually answer. So, one question number 1, question of percolation. Two, distribution of size connected component of any one vertex V. I start from a particular node. How many nodes can I cover if I were just to traverse on a graph which is connected? So this you should think of something which we have been hammering for the last 1.5. Something very similar, even though the process will be slightly more complicated. We started with one single individual and kept branching out. We'll very soon see that this appears something like that, but not the IID-ness will be the problem. The number of children you will be giving birth to, they will be IID. That's all there will be. Otherwise, it's a branching process. Okay. Another question we want to ask: connectivity. Which is harder, connectivity is harder or percolation?
What is the percolation question?
Percolation question is: does there exist a node V such that I define all this is or make sense? So there exists some vertex V whose connected component is of size whatever. Connected component is all the nodes you can reach from V. That's the percolation question. Connectivity question is for any U and V. U comma V, there exists. That's my connectivity. But there are no isolated nodes. I can go from any node to any other. And once I have connectivity, I can talk about diameter. What more can we do? Is there anything more you would like to ask?
We have stronger connectivities, right?
Sorry?
We have like 2 connectivities, 3 connectivities. Things like
Okay,
that.
what is two connectivity?
So, like vertex connectivities, right?
Uh-huh.
So how many vertices can you delete from the graph and still have the
That's too complicated. Those questions are studied. But Like too far down the line. But what you would have essentially asked is, so suppose there is a node U, there is a node B. What is the probability that I am at least connected to two of my neighbors at least? Possibly you could ask those kind of questions. Or there are at least two paths going from U to B, which are unintersected. So a complicated question, but you can ask. What you are asking for is more way more complicated. But those are very well studied. So this area is extremely rich. Let me ask you a very simple question. What is the probability with the first edge starts to form? What's the minimum probability?
First edge start.
One edge in this graph start to get formed. See, I have this probability P, which is an edge function. 1 by n. And I'm doing this how many times? How many pair of vertices there? N choose 2. But that many times I'm sampling this essentially coin. But there is a possibility that the graph is completely empty. So what is the smallest probability P such that there is at least one edge in this graph?
1 minus P raised to n choose 2.
You have to define what is the with high probability of expectation. What are you trying to do? So that's the first question you should be asked. When is this graph not ending? Because it's possible. So let's do something very simple. Today's class, even though results will be interesting, but the computations will be very easy. So let's say the event that the number of edges is greater than 0 in this graph. That's my event. So what are we after? We're trying to essentially find probability of A going to 0. If something happens, then probability of if something. And what we want is something of this sort. So P of n is the notation. So P is the probability with which n edge exists, and it depends on n. So that's why P of n. If I write just P, assume there's always P of n. Because if you make P constant, this graph is
No, n is the number of.
N is the number of vertices of this graph.
Yes.
And P is the probability with which an edge exists.
Okay. Yes.
Almost always, the interesting case is that P depends on n. So that is why we keep writing P of n. But if I drop this n, always assume that that depends on n. Because if you make P constant independent of n, the thing is just too trivial. It's just too dense a graph. It's always that you want to scale it down with it. 1 by n, log n by n. Those are the kind of regimes where this will be of interest. So what we are looking for is function P of n. When this goes to 0, I want this event to not happen. And P of n, P of n. What is T? So T is the threshold function you should think of. Then below T, so Pn is smaller than Tn, this is not happening. And if Pn is larger than Tn, actually it's going to infinity, then this probability is. So you should think of T of n as a threshold, or in your language, phase transition. So this is the phase transition threshold. That if Pn is less than Tn, nothing is happening in the system. It's actually a vacuous system. But as soon as you exceed it slightly, suddenly things go from 0 to 1. That's what that threshold is. And all of these are as n goes to. So this you should think of little of T of n. This should be slightly bigger than T of n. Okay. So now we're interested in when is P of A going to 0 or P of A going to 1, and A is defined to be this quantity. What is the expected number of edges? We really have very few things to compute here. So what is the expected number of edges?
Just to nice.
P. Is the thing, n choose 2 times P. And n choose 2 is roughly how much? N square?
Half
Half will not matter. Keep it on. So what is it telling you? P of n should be what order? No, so we know something, right? If a random variable's expectation is something, what is the probability is greater than 0? There's some connect, there is quantities of interest. What I want to count is probability of A. And what I know is what is the expectation of the number of edges. So this should have something to say about probability of this event. So this is the usual thing you do. If you want to say what is the probability that number of edges greater than 0, directly use Markov inequality. That's one way of doing it. But then what is it telling you about P of n? If n square by 2 times P of n is the expectation, what do you expect P of, so this should become constant at least. Otherwise, this is always going to go to. No, I didn't follow that. So what is P of n is what I'm asking.
1 n squared.
The expected number of edges getting is n square by 2 times P of n. So if P of n does not go down as n square, this is too fast. So the expected number of edges are going to go to infinity. You're very likely to see P of n going to 1. Similarly, if you prevent that P of n is smaller than n square of n, this is going to go to 0, and this should also go to 0. So T of n appears to be roughly t square by 2. But now can you nail it down correctly is the question. We want both directions. One direction you can prove directly that if P of n is some order, one of the two events should be able to show that either next quadrant 1 and 2. 2. So which of the two you can prove taking a T of n is equal to 1 by n square by 2. With expected number of values going to go to 0, what is the probability that A is going to 0? Right. What is probability A? It's a positive quantity. So necessarily what has to happen? The question is clear to everybody. Suppose I take P of n to be smaller than n square by 2, 1 by n square by 2. The expected number of edges is going to go to 0. If that happens, what happens to P of A?
Goes to 0.
Why? What you need to give me that insertion arm. A follows A implies B, but because of what? It's true. Just tell me why and proceed.
It's probability that the 0 edges goes out.
Yeah.
Which is A complement.
Okay. So just tell me what you're using to show that. There could be many ways of doing this. If the expectation of a random positive random variable is going to go to 0, what is the probability that it takes a non-zero value? That's all we are asking. It doesn't depend on the graph or anything. Markov, there is a problem. It's a greater than 0. So that will go down a division by 0. And that's where you have a problem. If it was a constant, you could have done it. But the idea is the same. So that was the other thing doesn't follow directly. So now, part 1, will humiliate. Some reason you're not seeing it right now. I'm to be sure you go home and see the video. Okay, speed of That's what I mean. Essentially, it's a positive random variable whose expectation is going to go to 0. So it's necessarily that the random variable itself goes to the probability of the random variable taking a non-zero value better go to 0. The other direction is not obvious. But if P of n times n square by 2 goes to infinity, then what happens? Then the expected number of edges is going to go to infinity. Does it mean that this is 1? That requires a little bit of guess. So here, try to use the Poisson approximation. See, what kind of random variable is the number of edges? A binomial random variable with n choose 2 trials and p of n probability. And as n goes to infinity, we already shown this binomial random variable approaches the Poisson random variable with the same expected value. So if you use that, what is the probability that the number of edges take value 0? So what is lambda? Lambda is nothing but n times pn. Or n squared. It's not n anymore. The total number of possible edges are n choose 2. So lambda is n choose 2 times p of.
I mean, the expectation.
So now, if I approximate it by the Poisson random variable with the appropriate lambda, what is the probability that a Poisson random variable takes value 0? That is simply e to the minus lambda. And how much is lambda? Nothing but the expected number. Then the Poisson approximation. Probability that number of edges is how much e to the minus lambda, the minus. Now, if that is going to go to infinity, where is this going? So this quantity is going to infinity. This is going. So you need this approach. Otherwise, it's very difficult to actually go from here to proving that this is true. So essentially, what we see is that Tn is nothing but n square by 2. So these are the kind of threshold results we'll be seeing throughout the most likely next month or so. These are the phase transition. And they won't be as easy as this. So this is just a. So what is this telling us? That this is the threshold at which you'll at least see one edge in this photograph. So the condition on having one edge in the graph, what is the expected value of the number of edges in the graph?
No, I mean, what is this expected value going to infinity? And how am I interpreting this
expectation of the number of edges. Now, if I take P of n such that this quantity goes to infinity, I at least get that the event that the number of edges is greater than 0 is probability 1. But if I go slightly below this, it suddenly is going to 0. That's what I said, threshold. Just below, so just below and just above means order wise. Forgetting the concept. All these results are order wise results. P of n at least has to be so much for you to even start talking.
For constant, it will always happen.
No, not constant. Forget about all this. P independent of n will never be interested. Here we are interested in saying how should P of n scale with n so that I can do something meaningful with this graph. This is telling you the first thing you should do is that it should be at least as much as n 1 over n square by. If it is below that, the probability with which you see anything in this graph is no. It's a meaningless graph below this threshold. So at least P of, so this is the starting point of addition. The P of n should be at least 1 over n square. Anything smaller, you're in. And that is intuitive. The expected number within 0. But we just need to make it. All right, so let's go to the most difficult winner or most complicated of my list. And amazing zero proofs are simple. So go to just to make sure that you're convinced that we should study all these things. So directly go to this question has to be easier, this question is easier. This question follows this, but I'll go to the connectivity question the first. Try to see what is the connectivity question. So now think of this hyperspheral graph as a branching process. So suppose I have this one particular vertex I'm looking at. What does it look like? What does the graph look like around this vertex V? How many edges does it come out? That process is very easy. What is the number of children does it have? See, there are n minus 1 possible choices and p probability p with which the edge exists. So this is nothing but a b of n minus 1 to 2. At least now from here onwards, what is going on? So I've started with one particular vertex. Let's say I'm connected to U, connected to W, Z, and rest of them I don't have connection. So possible choices were n minus 1 of these. There are n minus 1 nodes I could have been connected to for a particular realization. Let's say the 3 of them are connected. Now what happens starting from U? Now you could be connected to W. So let's say another level of n minus 1 nodes. So when I say level for that particular vertex, excluding that particular. So here V will be there, W will be there, Z will be there, except U itself. I see. Now what is the picture starting from here? What does it look like? It can get connected to W also. It can get connected to V also. What does it mean? That if I have a connection to V, what does it mean in terms of a graph? Suppose it gets connected to V again, as well as W.
We allow multiple edges.
So there are no multiple edges.
So it's a closed kind of thing. I mean, it's a closed trajectory.
Sorry. So okay, maybe I should avoid. Once it is connected, it's connected. Okay, I'll put some other. Let's see. So what is the difference between the usual branching process and now how we are viewing this graph starting from a particular vertex?
Nodes at the same level might be connected by one edge.
Somewhere down the line. Possible. Okay.
So there is no sense of generation.
There's no there. You can think of it that how the graph actually came about was I started from one particular vertex and started connecting. Is another way to see the same graph. So generation you can associate because I don't have to draw all these edges to begin with. I would say I'm starting at one particular vertex. Look at all possible other nodes. Just connect it to with each of them probability P. That's perfectly fine. So just think of the view from here. Now, compared to the branching process, how is it different?
So let's earlier, I mean, at the same level, you couldn't connect the same node. I mean, node that existed in the same level.
That was correct. But that was also not the case of joining things. Right? It was actually producing certain things. We'll have a labeled element.
Yes.
So in terms of that, think about it. How many new progeny can actually generate compared to the branching process? So think in this case, just number of edges going out. Does it depend on what has happened in the past? That's all I want you to put your attention to. In the branching process, it didn't matter how you reach there. In this process, it doesn't matter. So the chance that you can connect to a certain number of vertices, does it depend on the current number of vertices in any way?
Children of W in the second level and in the third level are the same. We know all.
No, just observe something, right? That the ability of U to generate new children is diminished because U is already connected to V. So V was a free vertex, let's say. It was allowed to connect to any of the other possible vertices. Now the fact that U is connected to V, the number of children you can give birth to, at least one node is out, which is V. So it's depending on what has already been connected. So U's ability to connect is constrained by an edge having been already been present between U and V. So this is not as simple a branching process as we had considered. There is some history dependent offspring distribution.
No, I think even in that case, so like it depended on the only the last step, right? I mean,
No, it depends on anything.
no, I mean, you could make the translation and stuff. But
Yeah. So the branching process we have been considering. We started with one individual. It gave rise to, let's say, 3 individuals. At this point, it didn't matter that this,
where it came from, yeah.
it is completely independent. Here it's no longer independent. That's all I'm trying to say. This presence of this edge is reducing the ability of you to behave as equally as we did. Because this is already been taken now. And this is going to percolate as you go forward, further and further. The number of edges which are already present will reduce the possibility of new edges being created. That's what will happen in this case. If you do an exploration on the graph itself. So it will look like a branching process, but with dependent offspring distribution. So we'll come to that, but before that, let's do the very interesting here. And this was actually improved by our machine learning. And 60. Sorry. So this is going to use ER graph. EN is equal to log n. Very clean there. What does it mean? That the expected number of nodes is how much for each vertex. So expected number of neighbors, let's call them. So each vertex has how many neighbors? On average, just log n. There are n minus 1 other vertices. The probability with which you can connect is log n by n, so it's roughly log n. For any vertex V, the expected number of neighbors that is sufficient for connectivity. For percolation, we'll see it's NG1 is sufficient.
No, I didn't understand. Can you repeat?
You remember the definition of Tn? That essentially Pn below Tn and Pn greater than Tn, the phase transition going to happen. So think of Pn essentially as log n by n. What we're telling you is that if you choose Pn to be smaller than log n by n, you will not have a connectivity.
I see.
If you choose Pn greater than log n by n, you have connectivity probability 1.
And so the expected thing
So
was
the
that
expected number of neighbors each vertex is going to see with this probability is nothing but roughly log n. So the takeaway is essentially that if the expected number of neighbors each node has log n, you should see connectivity.
So we will see connectivity, meaning whole graph would be connected.
Probability of connectivity is equal to 1 or tends to 1 as opposed to 2. And connectivity is well defined. That between any two vertices, there is a connectivity. That's what connectivity is. And I can reach any node from any other node. No isolated nodes. That's a necessary condition. They're not sufficient. Is it clear what is going on? What will is in fact prove is slightly stronger. That P of n is some constant lambda times log n by n. If lambda is less than 1, the probability of connectivity goes to 0. If lambda is greater than 1. Very sharp. Typically, you don't get these nice sharp results. All I'm saying is that you pick P of n with some constant times log n by n. If the constant happens to be smaller than 1, you can't have connectivity with probability 1. If the constant is slightly greater than 1, any number greater than 1, your connectivity is probability. Which is a stronger statement. There are so there's something inbuilt in the definition of Tn is order sense. I'm dropping all that. I'm saying 1. Much sharper than that. There you could have absorbed 10,000 times log n by n. Here I'm saying 1. Much sharper.
What would be the case of lambda equal to 1?
Yeah, that is probably a complicated case. What exactly happens at lambda equal to 1 typically is a difficult case.
And I didn't get this expectation value of number of neighbors.
So, okay, so what is the definition of a neighbor for a vertex V is? If there is an edge between U and V, I define them to be neighbors. So what is the, if P of n is log n by n, what is the expected number of neighbors you're going to have? There are n minus 1 other nodes. And with each of them, I am tossing a coin with probability P. So what is the expected number of neighbors I'm going to see? N minus 1 times P of n. So n is same as n minus 1. They cancel and you get log. Okay, to show that there is no connectivity, it is sufficient to show that there is at least one isolated node. Isolated node means it's not connected to anybody. An isolated node will definitely mean that there is no connectivity. So that's the probability we'll try to count. Let chi I to be an indicator dynamic variable to denote 1 if node I is isolated and 0. What the probability that a node is in fact isolated, that we can compute. So what is the probability of psi I equal to 1? All possibilities turned out to be, let's say, tails. If you think of heads and tails. Can you approximate this? The exponential. What's a good exponential to approximate this?
minus n minus 1 times p.
exponential e to the something. Of e to the minus. That p of n is smaller, so 1 minus x to the power n is an approximate.
In limit, I think it will be.
In limit and just a limit.
Yeah, everything is large number. And you can also write it as e to the minus. So lambda is always. Sorry, what is that? No, lambda is that parameter here. So P of n is lambda times log n by n. So that's what the lambda is showing. Use that, you get log n, which is n. This is arithmetic. There's nothing going on here. I'm just planting the value of P of n, which is lambda times log n by n. Okay, so now I have the probability that a particular node is isolated is n to the minus lambda. To show that there is no connectivity, what should I use?
No, this point.
So one particular node is isolated has this probability. Connectivity requires how much? That there should be no isolated. So what is the probability that there is at least one isolated? That's what I should be after. Here I am computing what is the probability that a particular node is isolated. So what is the probability that at least one node is isolated? Or you can first think of what is the expected number of nodes that are isolated. How much is that? That's just n times n to the power minus lambda. So now if lambda is less than 1, what is it telling you? That the expected number is in fact growing with n. Is that sufficient to conclude that the probability that there exists an isolated node goes to 1? Is it clear the path I am trying to look at? So what is the expected number of isolated nodes? This is a crude way of seeing why lambda is equal to 1, but when lambda less than 1 should not work and lambda greater than 1 should work. This is how much? N times n to the minus lambda. Now, if lambda is less than 1, this is going up. If lambda is greater than 1, it is going to 0. So that's a very crude way of saying that in one case you should not have connectivity, in another case you should have connectivity. But doesn't mean that you get what you want. You have to work a little bit harder to actually get what you want. So what can we actually do to show that the probability of connectivity goes to 0 as long as lambda is less than 1?
Why is it not sufficient?
This is just the expectation. Expectation has nothing to do with almost like what are we after? After a much stronger result. The probability of connectivity goes to 0. If you're happy with your expectation, that's your goals are to what's one way of showing up?
So if expectation goes to 0, then probability also goes to 0.
What do you want to show? You want to show it goes to 1. You want to show the probability of not having connectivity. That we should. Let's solve chi equal to summation of I is Is it? See, what are we after? X equal to 0. Chi. Is there any connection of this with respect to expected value of chi? Expected variance of chi. Can you connect these quantities on my right hand side to the probability of x equal to chi equal to 0? For any random variables, any positive random variable, is there a connection between probability of x of that random variable taking value 0 and its mean and the variance? Or the second one, whatever. So forget the variance, just think of second moment and mean.
Yeah, X is I.
Chi are they I? Think about it. That if that was true, a lot of things would have simplified that. So suppose I give you information that this particular node is isolated. Does it tell you something about other things? It does. Why is it isolated?
Because it's not connected to neighbors.
To anybody.
Yeah.
So that tells you that the rest of them also are not connected to them.
I see.
They are not independent. They were ideal things to have achieved. But just think of a simple relation between these three quantities. 1, 2, 3. Because this we have computed.
Yes.
And if there is some nice relationship between these, you could possibly also compute this. That's not too hard.
So why do you want to calculate this chi-square curve? I mean
No, suppose I want to control this event, this property.
Mhm.
I already know what this is.
Mhm.
Suppose there is a nice relationship between these three quantities. I could also, if I can compute expectation, it's quite likely that I can compute second moment also. And in which case I can solve this. But you know, not seeing this, it's a pretty simple elementary relationship between this. You can also do it from first principle. So that's correct. What is this correct? Or neither.
Dimensionally.
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 That's not true. Because as I said, possible.
Why is it not variance in the domain?
Yeah.
Sorry?
Variance.
You want to have a laundry list? So I claim that one of them is true if something else is true.
So you have a square missing in the second number. It's just you can just cancel one experiment.
I can. That's true. That's what I actually want to do. So under what condition do you think that is actually true? If I give you that the second thing is true. Well, suppose expected value of chi is roughly the variance of chi. Then what can I say? Then are you okay? So if not, you're not seeing this or you can't see it. This is a simple exercise for any positive random variable. Okay. Very simple. If you write it, if you open the variance, you will just get it. This is what I want to use. So what does it mean? This 1 over P of chi. This I already computed. All I need to show is this, that the variance of this chi is nothing but whenever I put this, it means I post a constant difference.
No,
So these are equivalent.
yeah,
So all I need to really care right now is to show this. Because once I have this I already computed. And this I know has a very nice relationship. What is it? 1 over 10 minus. So I can get whatever I want. As long as I can show the expectation of chi and variance of chi. I can just nicely relate. Okay. What is this is my chi? What do you think variance of chi is? Expectation was easy. What is second moment? If you can compute second moment, you can compute the variance also. Up to you, how you want to compute the variance. So essentially what will show that as n goes to infinity, expected value is same as the variance. That's what we really want. Not difficult exercise. Nobody wants to do. Okay. So what is the variance of chi? In terms of variance of chi is what is the look at cross terms. How many times? I multiplied j. Variance of each of them. At least all of them are identically distributed, so I don't have to compute different. Whatever value I get for one, it's the same for the other. So it is simply n times the variance of one of them. What is the variance of one of them? 0, right? Variance 0. You can binary. You know what a random variable is? Let me tell you deterministic. So we already have this. Which you could compute. So let's call it Q is equal to 10 to the power of 5. It's nothing but Q times 1 minus Q. 2 times n into n minus 1. Well, where there are and covariance of this one. Again, they're all identically distributed. And so this is algebra. I'm not going to spend too much time here. And times you get. So this you can compute Q squared P minus Q squared. Essentially, the covariance can be written as this is directly from here. This you can compute to be Q square over 1 minus. So what is the final number? You know the final answer. P is the usual P of n. Q is just n to the power. Okay. So for large n, remember lambda is less than 1. Where is Q going? As n goes to infinity, Q goes to 0. Where is this quantity going is what you want to show that as n goes to infinity, when lambda is less than 1, expected by is nothing but n to the power of 1. That's very not too much. So if you put like this, we just go back home and all the algebraic steps are not spent too much time. But essentially what we are trying to do is the following. You want to control this probability. And what do you want to show? That this goes to 1 or 0. What is the event chi? Then chi I is the event that there is an isolated. Chi is there is at least one isolated. So what should I want this to go to? Probability of chi equal to 0 should go to 0, right? So what does it imply? If suppose it goes to 0, what does it imply?
P connectivity is what?
Sorry?
If
There is no isolated.
There is one attribute.
there is a big one related.
Between complementary things.
There are no nodes. I can then they should be connected.
That is not a sufficient condition. Not having isolated node doesn't imply connectivity.
You want this to go to 1 better.
So that's a separate story. Suppose it's going to 0. Does it help me at all? Right.
The chi is equals to 0, the sum input. It implies that there is no
Okay. Is it useful as a question?
and the probability goes to 0, then
P chi equal to some non-zero value could have some weight then. So P chi equal to 0 equal to 0 is not useful, right? Because
Oh, so suppose I wanted to show that the probability of connectivity is going to 0. What do I want to show? In terms of isolated nodes. Remember the expected number of isolated nodes is going to infinity.
then this should be normal.
n times n to the minus lambda. Right? Lambda is less than 1. So the expected number of isolated nodes will be go to infinity. Now what is happening to probability of chi equal to 0 or greater than 0, whatever complement you want. So if probability of chi equal to 0 goes to 0, what is probability of chi greater than 0 go to 1? That's the event here. What does it mean? That there is no connectivity. Chi equal to 0 is not sufficient information. See, not having isolated nodes doesn't mean that there is connectivity. But having an isolated node definitely means there is no connectivity.
Why do you say that? I mean, having a, I mean, if you
Connectivity is not same as isolation.
no, if you
So
have,
suppose I have just stubs. I have this graph. This is connected to this, and this is connected to this. Nobody is isolated.
oh, okay, connectivity means, I mean, yeah, sure.
So all this is telling you the probability of x equal to 0 is equal to 0. That means probability of x greater than 0 is equal to 1. And that is the event I am interested in.
Yes.
So that is why sub lambda less than 1, all of this works out. So this is only a necessary condition that there should be no isolated. It's not sufficient. For sufficiency, we have to worry about all possible possibilities. But turns out that lambda equal to 1, if lambda greater than 1, we still work out. That is the amazing part of this. Typically, in most other non-trivial cases, you will see lambda to much larger, for which you will see something. Here, the threshold is exactly 1. That's the amazing part of this. Is it clear what we did? All we did was to look at this very simple event. That whether there exists a particular isolated. And we essentially counted over all possible that there exists at least one. That's all we have done. We showed that that goes to 0. Okay, so now the positive side. So now it's no longer true that you will just simply look at the isolated nodes and get some. You have to worry about lots of different. Okay, so let's look at the probability that the set of nodes 1, 2, 3. To the rest of the graph. Pick any k nodes and compute the probabilities that they are not connected to the rest of the graph. That means there is, so essentially for k equal to 2, this is the case. There should be no connection to the rest of the graph. So essentially it's just partition. So what is that probability? You can sound it at least. Or you can write it exactly. So how many edges go from a bunch of k nodes to the rest of the graph? There are k nodes on one side, n minus k on the other side. How many times? N minus k. K times n minus k, and there is a p. So p to the power this. That many edges. So the fact that it's not connected, what is the probability? 1 minus p times to the power k times n minus k. And how many such possibilities there are? N choose k. So for a fixed set of these nodes, what is the probability not connected to the rest of the graph? The exact thing, 1 minus p to the power, sorry, k times n minus k. Okay? You're not okay with that?
No, yeah.
Okay, so these are a set of k such vertices. Look at the rest of the graph. How many possible edges there are between these two? K on left side, n minus k on this side. So product of that. And each of them turns out to be tails. That's the only way in which you can not connected to anybody on this. So just 1 minus p power. K into n minus k. So good start. But there are how many such possibilities of a size subsets? N choose k. The whole graph, there are all possible ways in which I can pick k nodes. So probability that there exists a set of k nodes that are not connected. The rest of the graph. Is simply now tell me how do I control the probability? Sir,
It's not equal, right? What at an inequality, right?
this one.
And this here,
This
there
one.
exists.
Why? Precisely is many. It's both ways. Oh, so now tell me what should I control? I want to show that there is connectivity as long as lambda is greater than 1. I have written these events in a very nice way. Now tell me which event should actually imply connectivity. And that probability I want to go to 0. Okay. That probability I want to go to 1. So what is the probability that there is a disconnected or isolated set of nodes from this? I will do in a very particular manner. What I will learn, but taken any arbitrary k size subset and said what is the probability not connected to the rest of the net. Using this, what is the probability that there exists a isolated set of nodes?
We want this to go to 0 for all cases.
This is not sufficient to go to 0 for one case. That's what I'm asking. Using this definition of event, what is that event which will guarantee me that connectivity always exists? So I fix the k here. I'm saying look at all possible subsets of size k such that they are not connected to the outside world. Connectivity is much more than that. Connectivity will say there exists a k for which there exists a subset of size k.
Which are not connected.
Right. So what more I have to do?
Check this for k.
All cases.
So I should put a k, another k outside. And what does it entail? In terms of probabilities, if I'm taking a union, essentially I'm taking a union over all possible cases.
Wait, what is it?
Use this event to define a connectivity event. That's what I'm asking.
So I'm saying this should go to 0 for all values of k.
That's not sufficient. It's not sufficient. Why? For all simultaneously, not individually. That's the difference. So if you pick one particular k, it says okay, the probability that there exists no such k is 0. That doesn't mean connectivity. I want to for the graph simultaneously for all possible values of k. That means connectivity.
That is what I'm saying. For all values of k, I should.
For all simultaneously, right? Not separate. There are two different events. One is that I can claim that this event itself goes to 0 for a fixed k. That's a very different event. If I put a union inside, say for all k,
Yes.
it goes to 0. That's what I really want. Oh, so if I take that, why does it go to 0? When lambda is greater than 1. Remember, p is nothing but log n by n times lambda. Yeah. Can you convince yourself first and then convince me that this is working out? But how many possible choices of k do I need to check? Should I need to check k from 1 to n or something smaller is okay? N by 2 is symmetric. It won't matter. So in the worst case, I can take a union bound. Right. If I take a union bound and sum these probabilities from k going from 1 to n by 2, what do I get? Do I get what I want? Just stare at it for a while. And remember, p is log n by n times lambda. Disconnect. From the begin bound at most, it will become 1 to n by this probability. Anybody know? Graph being disconnected means that there is some k for which this is true. For this adding all those probabilities. Okay. Remember P is lambda times. All you want to show is that if lambda is greater than 1, this probability goes to 0. Can you convince me?
Why is there inequality?
Union bound, that's it. You don't, I don't have to worry about equal and unequals on this. They're actually dependent events, so you won't get equal. They're not disjoint.
Yeah, I was saying that in the second line also.
That's not true. That is actually disjoint.
Those are also not
Why?
disjoint events, right? Two different sets of k nodes. In that sense.
Okay, let's just give it to you. Might be too hard to, it might not be. So this. So who can convince me that this is going to 0? There's nothing to be done really. You just pick a lambda greater than 1. Something which you all know. If you apply, see, as soon as you see a factorial, what's the only thing you really have? There's nothing else. Okay. So if you apply Stirling's approximation, what do you get? I never remember what Stirling. I always have to look at it. You can never remember this one. Essentially, k factorial is not k power k divided by n e to the curve. That's the power. So Stirling's approximation for factorial is. Let me not use k is k to the power k divided by k to the power k. If you use that, what will you get here? And this also applies n choose k. N to the k divided by k by. This is what you really use. What have you seen this? Stirling's approximation.
The first one I have seen, the second one.
This is not approximation. You use this to. Right? This is not an approximation. Stirling's approximation is the approximation to the factorial. You apply this to this formula. Use your. Okay, so can you see it that why that is actually true? That lambda greater than 1 works. What do we get here? Power k by power k. Now P is this. This goes to 0. I'll leave you with that. So think of the bigger picture. What have we done? We have actually done something serious. We looked at the hardest event. What you could look at is a random graph. That is connectivity. Connectivity is a very serious issue. Every single node should be connected to every single node. It's a very, very harsh requirement. Turns out for this graph, handling that is not too difficult. And turns out that the regime in which it happens and the regime it doesn't happen exactly sharp. That is what the big picture is. It's a very simple thing. And how you go about it, always in terms of when you're trying to show that there is no connectivity, it's always or almost always trying to find what is the probability of isolation, and then putting a union bound around it. Okay. If one node is isolated with certain probability, what is the possibility of finding at least one isolated? Almost always that's how it is. This reverse side is almost always difficult. They show that there is actually connectivity. In this case, it turns out to be easy. What did we do? We did something very simple. We looked at what possible event there can be for this disconnected graph. So there is a bunch of nodes which are not connected to the outside. That probability we can control. How many possibilities there are for a fixed size set and choose k of that. And on top, is there any possible value of k for which that can happen? So that's why essentially the three union bounds. So two union bounds. From here to here the union bound, from here to here the bound. Most often, these becomes loose. And you don't get exactly sharp results. It's just that in this particular case, magically, we get exactly the sharp. The big picture, remember, is not lambda equal to 1. The big picture is log n by n. This will keep coming back to us. That roughly in most of these graphs, whenever we are looking for connectivity, we need log n expected number of neighbors within this log n, but for calculation, we need expected number of nodes to be just more than 1. In the branching process, what happened? As long as the expected number of progeny was greater than 1, it was probability of extinction was smaller than 1. That's precisely the big picture, right? That corresponds to percolation, does not correspond to connectivity. Connectivity you need order by almost all. So it's a very strict requirement. And the next few lectures we'll see percolation essentially will be tied up with a branching process and it not being extinct. And that is why P of n is equal to slightly bigger than 1 over n is sufficient for that. But here we need log. This is one big picture we should take away. That for connectivity, we need order wise more probability. And that very often turns out to be log. While for percolation, all you need is the expected number of neighbors should be greater than 1. Even though it doesn't precisely correspond to a branching process, but that's what we'll do. What we'll do next is we'll lower bound it with the branching process we can handle, we'll upper bound it with the branching process we can handle. And essentially it will be a sandwich. The two process is not a nice process. It will be lower bounded and upper bounded by a nice process, which we know. That's what we'll do. But insanely enough for connectivity, we don't have to do all that. But in the process, we have lost the factor log n. If you wanted to do 1 over n, it tells you that you can't do it. You need log n. All right, let's start with it.